Guys and girls, it's Know It Time! Know It Time!
So I want to do a quick recap. Last time, I taught you rules for continuity. Okay. And there was 3 main sets of rules that you have to work and memorize. But for today, I want to push it a bit. Now this is called how can you determine if something is continuous, if a function is continuous on an interval. I'm going to give you a scenario. We're going to draw any random graph. We'll call this function right here. This is a very basic function. We'll call this number maybe -2. We'll call this number 3. They're going to ask you, and this is f of x, is the function continuous on the interval -2, 3. And this is what I want to focus on today. They're going to ask you, is this function continuous? Well, most of you will look at this and say, that's easy. It is continuous. Because why? I have a nice straight curve. There's no missing points. And I can find the limit of everything. So we can say, yes, it's pretty easy. If I give you a graph, you can actually do it very easy just by looking at it. But the problem lies, what if I give you an equation? Okay. What if I give you f of x equals to 1 minus x squared? And I ask you, is it continuous? Yep. Continuous on the interval -1, 1. The problem with this is this. I don't have all day to plug in -1, 0, 0.5, and I try to find every point. We can't graph this because you don't have a graphing calculator. So there has to be some algebraic way to doing this. And there's actually a new definition you need to worry out. This is a new theorem. Here's what it says. Put a star beside this one. Star. A function f is continuous if, continuous on an interval if it is continuous at every number in the interval. Every number in the interval. But again, this theorem doesn't really prove anything yet. So I'm going to teach you a bit more about this theorem. If I have an interval -1 to 1, let's focus on this right now, -1 to 1. What I'm going to do is I'm going to break it down. In order for me to find out if it's continuous on the interval, because it says a function is continuous on the interval if it is continuous at every number in the interval. So I'm going to break it down into two really left side continuity. and right side continuity. Because if I can prove that from everything continuous on the left side, continuous on the right side, we're done. Right side continuity. Because if I prove it, if it's continuous from the left side, continuous from the right side, we have a continuous on the interval. So here's how we're going to do this. I'm going to break this down to left and right side, and here is the tricky part. I'm going to go lim. If I think of this, let's just draw a random graph right now. Just draw any standard random graph. And put in -1, put in 1. This graph could look something like this for just a random graph. So what I'm going to do is I'm going to do the right side first, or I should do the left side. If I'm going to do the left side, that means I'm approaching this graph this way. So what I want to focus on is lim. As x approaches 1 from the left, because that's what I'm calling the left side continuity, for the function f of x, which is in this case f of x. So this becomes lim as x approaches 1 from the left of 1 minus x squared. I'm going to pause it, let you guys figure out what is the limit going to be. So if I look at this, I just plug in, and notice when I find the limit, lim, as x approaches 1 from left, I can just sub it in. 1 minus 1, which equals to 1. Would you agree also that the lim, as x approaches 1 from the left, equals to f of 1? Hey, it satisfies my 3 conditions. Therefore, we can say this. The graph is continuous from the left. Therefore, the graph is continuous from the left. I just proved to you it's continuous from the left. So instead of proving every point, I would say that why don't we just take it and say prove it's continuous from the left. Now what you got to do? Prove it's continuous from the right. If I want to look at the right side, here's what's going to happen. So I'm going to look at it this way, right here. So I go lim. As x approaches, now notice I'm using -1 from the right for f of x. Guys, I want you to take it and run with it. I'm going to give you a little bit hint. I go lim. As x approaches -1 from the right, this would be 1 minus. And the beauty about this equation is I can just sub it in. And if I sub it in, what's my limit going to be? Anyone know? 1. And notice one thing. I can do lim as x approaches -1 from the right. I got it by just subbing in -1. Therefore, it's continuous. The graph is continuous from the left. Oh, sorry, from the right. From the right. Now, according to my definition, if it continues from the left and the right within the interval, it is continuous within the interval. And we can write a conclusion. Therefore, since the function is continuous from the left and right, it is continuous in the interval -1, 1. That is how you prove something is continuous within an interval. We're going to try that with that question number 13. that you guys had and you couldn't do. So let's look at number 13 and let's do this as a class right now. So numero 13. Prove that it's continuous. F of x equals to x root 16 minus x squared negative 4 comma 4. I'll give you about 8 minutes. Right, I think that's enough time for you guys to practice. I'm going to break this up. In order for me to prove it's continuous on an interval, I'm going to break it up into two parts, left side and right side. Left side, right side. Again, you can do it in any order you like, right side. So I go lim. As x approaches 4 from the left of x 16 minus x squared. And if I can sub in 4, I sub in 4. And in this case, I can easily sub in 4, so which gives you 4, and this will be 0. Which gives you 0. And I say this, look, lim as x approaches 4 from the left equals to f of 4, because it's the exact same value. So which means it is continuous from the left. Now we do the exact same thing for the right, but I'm not going to do it because I can let you can figure that out on your own, and we write our concluding statement. That is proving continuity within the interval. The last part of continuity is something called the intermediate value theorem. Intermediate value theorem. And this is the last part. Intermediate value theorem. And this theorem states this. It's straight from your book. I'm going to give you a textbook definition. A lot of you won't be able to understand it, so I'm going to just explain it after. It says, suppose that f is continuous on the closed interval. So everything now comes together. We're talking about intervals now. A, B. And let n be any number between FA and FB. Then there exists a number C in AB such that f of C equals to n. Whew. By the way, does anyone know what the heck this is talking about? Can anyone decode math? This is actual theorem. See, what this is really saying is this. First of all, the function has to be continuous. This is why I've been teaching about continuity. If it's not continuous, this theorem does not work. We're going to draw a grid again. And I'll explain to you in pictures what this really means. Let's draw a simple one like that. It says this. Suppose f is continuous on the enclosed interval a, b, So let's say this is A. We'll call this A. We'll call this B. It is continuous on this interval because it's a nice curve. Let n be a number between FA, FB. Actually, I'm going to change it up. This is a bad example. I'm going to change B to be here. We'll call this B. So that's B. They're going to say this. Let n be any number. So this point is FA. This point is FB. So it says n be any number between FA and FB. Somewhere between. Doesn't matter where. Choose a third point. We'll call this point N. Okay. They're saying this. If this piece is continuous, therefore, there has to be a number C in between A and B that gives you this N value. Some of you say, Mr. No, isn't that obvious? If it's continuous, it should give you, there should be a number C. It is obvious. This is one of the most obvious theorems there is. And someone actually wrote it, and they call it the intermediate value theorem. Okay. I'm going to give you an example how we use it. And we're going to apply with this. It says this. Show that there is a root. There is a root. So there's a lot of things, there is a root, that is so silly and stupid that people write it, that no one writes about it, and then when they do, they become famous. Let's wrap this up. So show that there's a root between 1 and 2 for the equation for the function 4x cubed minus 6x squared plus 3x minus 2 equals to 0. When it says show there's a root, which means show that it passes through 0. Passes 0. That's what a root really is. Passes through 0. Through the x-intercept. I'll explain to you how we're going to use the intermediate value theorem. So I want you to say prove there's a root between 1 and 2. Well, first of all, we got to figure out, is this function continuous? Is this continuous? And the answer is yes, because it's a polynomial, so therefore your domain is everywhere. Yes, because domain is all reals. So there's no point where you don't have it discontinuous, all reals. So what they want to know is this is continuous. And this graph is a cubic function. It's going to look something like that maybe. Because this is a cubic function. I want you right now to find f of 1 for me. Go. Because it says we need to know what f of a is. Then we need to find what f of 2 is. Take a minute, find f1. f1 is negative 1. And how you just sub it in. f2 is 12. You just sub it into this equation right here. See, here let's put this label as 1. And we'll call this point 2. Somewhere here. So by the intermediate value theorem, it says this. Because this is continuous from negative to positive, it has to pass through 0. You cannot go from negative to positive without hitting 0. I'm going to say this. According to the intermediate value theorem, to the IVT, the function must pass through 0 through 0, okay, when it goes from negative 1 to 12. You have to hit 0, and that's what it's saying. It says there's a point C. I'm not asking you to solve it. I'm asking you to prove there's a point C that it has to pass through. And that is called the intermediate value theorem. And that wraps up your work. for this unit. Your homework. Page. And I'll give you the whole after lunch to practice on this, guys. 114. Numero. 43 to 46. Plus, after lunch, you have your quiz corrections, and then you have your chance to practice and catch up today.